Neurotransmitters are very important. They determine how we communicate with our nerves. And we'll show you some pathways coming up here in a minute on how the nerves can find their way to different parts of the brain or different parts of the body, either by converging or diverging into those different areas. Things like nitric oxide. Nitric oxide is important for a lot of things, but in the brain it does different things than it does in the body. In the body it stimulates the blood vessels to expand and causes them to have increased blood flow. Nitric oxide is one of those things that stimulated increases with Viagra and Cialis. That's what this neurotransmitter does for that, and for the brain it does different things. GABA and glycine are usually inhibitory. These are chemicals that inhibit things from happening. So if you have two nerves coming together, one of them could be inhibitory and the other one could be excitatory. When the inhibitory dumps its chemicals like glycine onto that excitatory nerve, it quiets it down. It squishes it so that it doesn't create an impulse across. Glutamate is excitatory. It's another chemical that will stimulate other nerves to work better and faster. And then acetylcholine is the one we find in our muscles and in our heart. Very important one. What we have going. Now, we can have what they call neural pools, where impulses come into a certain area of the body, and then they can move out into different parts of the body in different ways. So we have a single presynaptic fiber that's coming in, and then it will stimulate other fibers in different ways. We have discharge zones and facilitation zones that help us to create that movement of impulses. So in this case, we have this little presynaptic fiber coming in here, right? It's got myelin on it. And what it does, it has little divisions to it that will stimulate or that will synapse with other nerves. And then they, in turn, will send the signal out. So we can spread it out. So we can have one nerve coming into this area, and then it spreads out to the rest of the brain, or the rest parts of the brain. Okay? Everybody get that? That covers the whole brain then. It doesn't have to just be one nerve to one part of the brain. We only need a certain number going up, and then we spread it out as we get through. We have diverging circuits where we diverge, just like we showed there. They could be sensory, they could be motor, either one. But we have the input, we have one nerve coming in, sending signals to another nerve, and then they in turn will send signals to others. They diverge off into many, many, many nerve endings. We have converging circuits. Instead of having one coming into that area, we have many coming in, and then they will converge onto one. So we have, in this case here, we have input one nerve, 2, and 3. All right, all these nerves are coming in, and they input information to this one nerve. And then that sends an output to someplace else. So we could have this for different areas. Say let's go into the brain. If you have a diverging one, all the information comes into the thalamus, and then it diverges to the different parts. It'll go to the amygdala, it'll go to the prefrontal cortex or something, wherever it needs to go. It's transmitted to those areas. Or in turn, we could have many nerves that are being fired that come back and send a signal down to the big toe. We don't need 100 nerves to make the big toe move. We just need a few. So we're going to converge it down into the usable number. We have reverberating circuits. These are really important, especially this time of year, because these are the ones that help you remember for your long-term memory. Once you get something in your brain, it reverberates back and forth in these nerves, and you'll remember it for the rest of your lives. It will haunt you for the rest of your lives with anatomy. Right? You'll wake up the day after your final, and you go, "Oh, I remember." So it'll be good. But we're constantly, it's a kind of a loop mechanism. The information goes down, and it loops back up. It's kind of like deja vu. Remember We talked about deja vu, where it's kind of a repeat of what you actually see. Something in your brain, you see that image, and then it circulates back very, very quickly, and you think that you've seen it before. Right? We also have a parallel after discharge. So we have two different ways we can communicate. So we have the input nerve coming in. It sends a signal to the output directly, or it can go in different directions and stimulate in different ways too. All these little nerves could have connections coming off, stimulating other parts of the body or other parts of the brain. So we can have a very fast response, or we could have more of a widespread response because of this parallelization of the nervous system. We have different ways of processing. We have cereal processing. That has nothing to do with oatmeal or Frosted Flakes, right? It's a different type of cereal, right? Somebody's hungry? So we have input travels in a specific destination. They work in an all or none manner. Your nervous system is all or none. It either fires or it doesn't fire at all. We have the reflexes. How do we come out with the reflexes? We're going to be doing reflexes again tomorrow. Did everybody get done with their reflexes in lab the other day? Did you find somebody that had good reflexes?
I did.
So we'll be finding those. So somebody tell me the way that reflexes work. Jeff, how do reflexes work? You seem like you got something to help us out with. How do reflexes work? Give me the process the reflexes are working.
Okay, so you get the stimulus.
Okay.
The receptor takes that signal and it receives it first, and then it sends it on up to the brain through electrical signals.
Okay. But does it go all the way to the brain, or does it short circuit and come back at first before it does that?
I guess it's short circuit.
Comes back first, that's right. So it goes up to the spinal cord, goes across the spinal cord to the motor areas of the nervous system, and then back down to the quadriceps if you're going to do the knee, right?
Yeah.
So we have the components. We have the receptor, we have the sensory nerve, right? We have the inner neuron that goes across the spinal cord, and then what do we have left after that? What makes it move?
Muscle.
Right, so we have a motor neuron and a muscle, right? We call that the effector. So that's the quick reflex. That's what happens every time you thump somebody with those little rubber hammers. That's what you're doing. You're eliciting that response. Now, at the same time, though, that information is going up to the brain, and that's when you get that, oh, ouch, that hurts type thing, right? Especially if you had that hard hammer. Didn't you guys have that hard hammer?
Yeah, we
So reflexes, automatic reactions. Babies have those reflexes. Remember we showed you that video on the little babies, if their arms will flare out. They're really cool when you do that. You stroke their back, and they're wet, they move their arms out, and they make a noise. You know, or you put your fingers in theirs, and they'll grip you. Those are reflexes. That's all done because they don't really know the difference. They can't tell the difference, and they can't stop that. It's just like if they're urinating. You know, little babies can't stop their urination. So wetting the bed is not something that they can stop. You hear people all the time, the kid wets the bed and the mom and dad, get after them for doing that. Well, they can't stop it. They're not mature enough to be able to do that. Eventually, their body will overcome that, and they'll be able to do it until they're about 80 years old, and then it goes back the other way around. So it just kind of goes that way. So this is really what Jeff was talking about. The receptor, the sensory nerve, the integration center. So we have all these things. The receptor is in the knee, right below the knee, in that tendon. Then it comes back to the spinal cord, goes across the spinal cord with an inner neuron, and then down the motor neuron to the effector, which is the muscle. At the same time, the information is going up towards the top of the brain, sending the information up that way. So we get completely covered both directions. Now, as we are developing as in babies and as a fetus, the brain is one of those things that we have to be very careful with. If you or messing around with drugs or alcohol or even smoking, you can affect the baby's cognitive abilities later on in their life. So we want to make sure that you take care of yourself as much as you can. And it's not just the girls, it's the guys also. They found out through testing with epigenetics that if a guy is on drugs prior to getting conceiving, that can affect the baby also. Question?
What about, I've seen videos of like pregnant women working out. Is that bad for the baby? Like, I saw a pregnant woman, she looked like she had a six-pack, but she was pregnant.
Too much can be detrimental. Too much, but you can walk, you can jog. So especially if you've been active all that time, you can stay somewhat active throughout pregnancy. But you can do too much too. You can hurt your back because the weight and the change, and you're also taking nutrients from the baby that may need. So if you're good at watching what you're eating, the number of calories, types of food that you're eating, lots of calcium, rich foods, those types of things, you can probably do a lot of different things. And it's been that way since cavemen and cavewomen, right? They've had to work, and it's just none of those processes. Very few women can just sit down and put their feet up and say, okay, 9 months from now I'll have a baby. It doesn't work that way, not in our society, right? So we won't be doing that. So development, the neural tube comes out first. That's what and it wraps itself around. That's why the spinal cord has a little hole in the middle of it. It kind of wraps itself around itself. And as we go through this process, the nerves develop, one of the first things to develop. About 2/3 of the neurons die before birth. So we actually have more neurons, more nerve cells before we're born than we do afterwards. And as we age, we actually lose nerves. They die just like anything else. They go through apoptosis, and then since they're not meiotic, they don't replace themselves. So the process is constantly deteriorating.
So after birth, how many neurons do we have? Or do die like in average lifespan?
Do they die? I couldn't tell you a definite number. I don't know. That's a good number. Depends on what you do too. If you use a lot of alcohol or drugs, you're going to kill a lot more of them. So, and then if we squish your hand or something, you're going to kill your nerves too. So they're dying. Many of them dying at the same time. Okay, so that's the end of that chapter. So now we're going to